we've already talked about how do you write a K. That wasn't too bad. We also talked about how do you write a Q. So I want you guys to get these steps right down in your notes about how do you find whether something's at equilibrium or not, and how much change would it take to get to equilibrium. Like, what has to happen? Do you have to add some reactants? Do you have to add some products? Which way does it flow? So y'all get these in your notes. Pause now. This is the first example that I want y'all to look at. Go ahead and get this down, and we're going to work it out step by step, showing you how it works. But in order to do that, you guys need to get these numbers down. Here's my balanced equation, and that was the first step. Write the equilibrium expression. K is equal to products over reactants. K is equal to products over reactants. The 2, that one right there, comes from the balanced equation. That's the number in front of HI. What's your next step? List the initial concentrations and build yourself an ICE table. So let's look at an ICE table. Okay, you can stop it right here and get this ICE table down. Notice I wrote everything across the top, reactants and products, and then I wrote ICE down the side. It's called an ICE table. I stands for initially, or in the beginning, what was the concentration. C stands for how much it changes, and E stands for at equilibrium, what is it going to be. So let's look back at the original problem and find some numbers. It told me I had 1 mole in 1 liter of each one of the reactants and the products. That's where it starts at. So what I have to know is right here, is that number going to get bigger or smaller? Is this number going to get bigger or smaller? What is my change? To do that, I have to find a Q. See if you can find a Q. Remember, Q is just the concentrations where we are now, in the beginning, initially. I plug them into the same expression as K, so I get 1 squared over 1 times 1, and that's obviously equal to 1. Now, go back and look at the K value. K is equal to 100. Q is only 1. Does that mean we're at equilibrium? Of course not. How do I get that Q closer to K? How do I get that number bigger? How do I get it closer to 100? Well, obviously, I need to make the top number bigger and the bottom number smaller. And that will give me an overall bigger answer. So, I know that I'm going to have to use up some of my reactants. I'm going to lose some reactants, and they're going to turn into products. This is 2x because it's going to go up by 2x because in the balanced equation, it was H2 plus I2 equals 2HI. Then for the equilibrium expression, it's easy. Let me show you how to fill it in. This would be 1 minus x. That would be 1 minus x. This would be 1 plus 2x. Right? In the last steps, I know my equilibrium concentrations, 1 minus x, 1 minus x, 1 plus 2x. Substitute them into my expression and solve. And let me show you how to do that. Here you see my equilibrium values back from my ICE table substituted into my expression. I knew my K value was 100. Now all I have to do is solve. All right, to solve this, what I need y'all to see is this is just perfect squares. Take the square root of both sides. Take the square root of both sides and see what you get. When you take the square root of both sides, that's what you get. All you have to do now is solve for x. We found x is 0.75. All I want you to do is go back to your ICE table. Go back to your ICE table and plug in for x. Okay? See, plug in x is equal to 0.75 and see what you get. At equilibrium, x is 0.75. That's what I solved for. So at equilibrium, my concentration of H2 is going to be 1 minus 0.75, which is 0.25. For I2, same thing. The concentration is going to be 0.25. At equilibrium, my concentration for HI is 1 plus 2x. 2x is 1.5, so this is going to be a total of 2.5. So at equilibrium, the concentration of HI is 2.5. The concentration of H and I are both 0.25. And if you wanted to double check yourself, you could just plug this back into the equilibrium expression and see if you're right. We had that K is equal to HI squared over H and I. And just to double check yourself, let's plug in what you got. K is equal to 2.5 over 0.25 times 0.25. And remember what we got for a value of K. K was 100, right? That's what was given to us in the problem. Well, is that right? Sorry, that should be 2.5 squared. Is that right? Well, of course it is. That's right. So we did it the right way. So at equilibrium, the products far outweigh the reactants. There's way more product, there's way more HI than there are reactants. So if we wanted to make this look like a fishbowl, not a fishbowl, an aquarium again, if we wanted to do that, imagine what that would look like. All right, here are your choices. This is choice 1. Would it look like this? If there are way more products than reactants, would it look like this? That's choice 1. Or would it look like this? This is choice 2. Which one do you think shows that there are more products than reactants? If you said choice 2, then you're absolutely wrong. If you said choice 1, you're absolutely right. Good for you. But you can see they're both still at equilibrium. It's just there's going to be way more products than reactants. You can put that divider anywhere you want to. Okay? And you can make it almost all products or almost all reactants. You can make it where it's dead even. That would be a K equal to 1. When K is bigger than 1, you have more products. When K is less than 1, you have more reactants. So if you had a whole lot of products, that's a K that's just huge. It might be 1,000,000. And that just means there's a whole lot of products. I want you to take example 2. I want you to go ahead and write an equilibrium expression. Write a K. The equation's already balanced. Write a K. Write an ice table for this. Write down your initial values. It's 1 mole in 10 liters of N2O4. That means you have no NO2 to start with. Initially, that'll be 0. Figure out what goes in the ice table. Take a stab at it. Come in with an ice table already. Come in with an ice table ready to go, ready to look at. All right? See if you can solve it. See if you can reach the very end. Stupid computer. See if you can reach the very end. If you can, that's fine. If you can't, that's fine too. But the most important part, can you write an equilibrium expression, a K, and then can you also write an ice table and work on finding it? And I'll see y'all in class.